Hello, everyone, and thank you all for joining here today. And welcome to Undefined Limits. We're basically tackling the integration of mathematics and AI, and we're celebrating the International Day for Women in Mathematics. So, this event is brought to you by Young for STEM and Code with Sarah. And together, we're diving into a topic that sits at the intersection of both possibility and precision, because mathematics really powers modern AI systems. So, from graph theory to modeling and to the math behind every algorithm, we'll be tackling that today. And make sure to stay until the very end to receive our exclusive graph theory and AI resource kit. So, without further ado, let's get started. What powers AI? So, we have the big three, basically, the big three triad, and linear algebra, calculus, and probability are basically the mathematical foundations of every major AI system. And if you felt that AI is just abstract theory, then you should definitely rethink again because these are basically the tools we use to build, optimize, and even explain intelligent systems. So, starting off with linear algebra, it's basically the math of vectors and matrices. And the way you could think of it as the language of data because every image, every sentence, and even every audio clip, when you feed it into an AI model, it gets translated into numbers. And guess what runs the show behind the scenes? Obviously, matrix operations. So, linear algebra is really crucial. Next up, we have calculus. I'm pretty sure you've all are familiar with calculus. We have calculus 2, calculus 3, and even calculus 4. Basically, calculus helps us understand how things change in AI, and we use it to optimize models, minimize loss, or even update weights. And basically, what we do is we try to teach the system to learn from its mistakes. So if we don't have calculus, we know calculus is all about derivatives, right? Then we won't have back propagation and we won't have deep learning. And finally, we have probability. And basically, probability is all about uncertainty. And AI isn't deterministic, it usually deals in predictions, confidence scores, risks, and outcomes. So if you ever seen a model saying, hey, I'm 86% sure this is a cat, then that's literally probability doing its thing. So those three, they all form the big three, and they're not really concepts. They're the math inside every algorithm. So this is your go-to toolkit. Now, before diving in, let's tackle a common misconception is you don't need mathematics to get started with AI, which is wrong because AI is all about mathematics and we'll see that in a few. So do stick tight. We'll see how mathematics and AI are related in depth. But before diving in, let me make just one thing clear in case some aren't familiar. An algorithm is basically a step by step defined set of instructions. So, and basically, an algorithm would have an input and output, edge cases, and this is basically what an algorithm is. And you will see in a few how to write a great algorithm. So, what is AI? When we speak about AI, you have to think of two things. First off, you have to consider uh, perceiving and learning, as well as deciding and acting. So let's just zoom out about the text box definition of AI and think of those a bit. So this is the cycle that we have. What happens is we take data, whether it was text, images, sounds, figures, patterns, etc. And what we do is we try to make sense of it. And then later on, we do something with that understanding. Okay. So we recommend the next, let's say we're trying to recommend, YouTube is trying to recommend the next video that will show up on your feed or Instagram or TikTok. That's literally just AI doing its thing behind the scene. It's perceiving, learning, deciding, and acting. Okay, but we do have a catch here is this loop basically doesn't just run on magic. Like it just doesn't exist like that by itself. Because behind every decision, we have something that's called logic. We also have structure. And we do know that mathematics is all about logic and structure. AI actually began in 1950. Basically, the revolution of AI all started with a mathematician, and he dared to think or to actually ask, can machines really think? And the rest was really just history. Who here has heard about Alan Turing before? Feel free to drop in the chat box or just raise your hand. Okay, so I believe no one has heard about Alan Turing before. No problem. Basically, he was a famous mathematician in 1950, and he was the uh, first one to actually start the AI revolution. And after that, the AI era started blooming and everything. And really, AI at its core started with a mathematician, not at a fancy lab, not at a fancy server. It all happened with a pen and really just a radical question. And we're actually still chasing that answer till this day. So there are obviously many definitions of AI floating around. But the European Commission defines AI as systems that perceive their environment, collect and interpret data. They also reason and make decisions. And then they try to achieve a certain goal. So, what that basically means is it senses what's happening around it, it understands and processes data, and also it tries to reason to make a choice. And this basically this process is all powered by algorithms, mathematics, and data. So it's really not just a black box or some sort of magic. When speaking about AI, I usually prefer to define AI and let it fall like within those three sectors, you could say. So you shouldn't throw everything into one basket, obviously. And while there are more, but they usually all fall with those or even intersect with those. So at the top, we have rule based systems, and these are basically just relational, basically algorithms. So it's basically hard coded logic. There wasn't learning, basically just if statements, and it basically just follows instructions. That was popular back then. We also have machine learning, and we'll see an example in a few. So basically, machine learning, what happens is we have a system, and we don't tell it how to solve a problem. They should figure out on their own by learning from data. So it basically is just models that improve over time based on certain patterns. Next up, we have deep learning. or some people just really say neural nets. So it's basically where neural networks come in, and it's actually just models inspired by how the human brain works. And really, it's the core of what powers voice assistants, image generation, and even tools like GPT. So, as mentioned, most of the AI applications you hear fall into one of those three categories, or intersect across them, or even base upon them. So when someone says, "Hey, I'm working in AI," ask them, "Are you training a model or are you building a neural network?" Because it matters. There's also some other fields, but those are the basis, literally. So let's start with our first example for today, which is a house prediction example. So we have the problem statement here. We have a house and we're trying to guess the price. Okay, we need to sell it for someone who's interested, and we have to put a fair and reasonable price. So usually what you would do is maybe look at the number of rooms, maybe look at the location, the number of windows, or even just at the age of house. So there are several factors to consider here. Okay, so this is our problem statement, and this is how we could try and predict the price of a house. What we would do, the high level overview, is basically taking an input, training the model, and then predicting. Okay? Now, we'll tackle each step and actually explain what's happening. So, in the input phase, we have our data. This could be, as mentioned, the number of rooms, windows, or even the age of the house. So those are called features. We're feeding them into the model and then we're training the model. This is where the training phase comes in. And what happens is the model looks at patterns in that data and starts learning the relationships between those features and the actual house price. Here we're uploading labeled data to the model. We're telling the model, "Hey, you have this number of rooms and you also have this number of windows, then the house would cost this amount." So the model would try to learn from this data. Let's say we have seven windows and three rooms, then the cost of the house would be, let's say, 1K something. So the model would see the pattern, try to understand the pattern and get trained on that pattern. And finally, we have the prediction. So in the prediction phase, the model can take a brand new house that it has never seen before and estimate the price based on what it learned earlier. So, this is just one type of AI. Basically, this is a classic machine learning problem, and this is the general flow. This is what happens usually. Okay, now let's dive in into what's happening in the input phase, which is where our features come in. So, what is really being fed into the model here? We're giving it pictures of houses or maybe long descriptions. This is all data, and specifically, we're giving it rows of data. And they're usually called feature vectors. And each one holds the fact about the house, number of rooms, number of windows, etc. But they're all represented in a numerical form. So, who is calling the shots here? That's literally linear algebra in the works, vectors and matrices. Okay? So, everything gets packed into vectors, matrices, and this is what our model understands. It basically understands vectors and matrices. Okay? So, this is the first step. Next up, we have the training phase. This is a specific example here. Of course, this could differ. So we got our input data in, we got the vectors in to the model. Now, the question is, How does the model learn? So, in this phase, the training phase, the model tries to figure out the best internal settings, also known as weights, to make accurate predictions, maybe. So, it looks at the difference between the prediction and the actual answer. Then it weights those weights to reduce the error. And this is actually called the gradient descent. Okay. And that's basically what's happening in the training phase. And this is where derivatives come in, basically calculus. So the model is literally using the slope of the error curve to decide which direction it has to move in and how much. So this is literally pure optimization powered by mathematics. Next up, we have the prediction. And here we have the dot product. So, how does it actually predict? We have this common example that I'm pretty sure everyone has seen before. So, basically, linear algebra again. And we're specifically talking about the dot product. It's the core operation that connects the input and the learned weights to actually give us an output. So, even at the prediction phase, we're still in the math territory. Okay? So, this is just a basic example, of course. Before diving into some other core ideas, just a quick question to stir things up here. Uh, is it true that you only need calculus, linear algebra, and probability to dive into AI? Who could answer from the attendees? Feel free to drop the answer in the chat box. Okay, we have an answer from Roa. Thank you, Roa. Who else? Based on what you guys have heard, or maybe just try and guess. Okay, we have another answer from Paula and Rihanna. Okay, that's great. It basically depends. Like, it depends where you want to proceed. We'll see that in a bit. But good, Pav. It's not true that we need to only know those because we're in the era where AI is constantly evolving. And we've seen several AI tools maybe replacing or automating tasks that web developers can do. It can even create a static website. It can even help in the UI UX part. So we are in the AI era and everything is evolving all around us, right? So what we should do is to try and adapt and evolve as well. So basically, the big three, linear algebra, calculus, and probability, are your entry level passport. Sure thing, you can become an AI engineer by knowing those. But you would have limited options. And what do we really mean when we say limited options? So you could use ready made machine learning tools to maybe train and test simple models, or even you can tweak pre-built AI models with small data sets. You can even read accuracy, loss charts, etc. So these concepts are cool, and many entry-level jobs require that. In fact, even some mid-level AI engineer related jobs are based upon that. Like you have to understand those to actually dive into AI because the best way to ensure that you're a great AI engineer is to have background and be familiar with those, right? But just as everything, this is your entry level passport. If you're thinking of evolving, then you sure thing need to learn new stuff in order to, let's say, acquire a new passport. So one passport really just is limited. It takes you to specific places. But here we want to grow. So Literally, those are just the tip of the iceberg. Let's say you plan into diving into AI further, you plan to be the next Alan Turing, for example, or you really just really want to understand what's happening behind the scenes, maybe try and optimize the existing models, maybe make a breakthrough. Personally, my recommendation is, if you've got the passion and if you're interested, then definitely you need to dive into some other topics because those are enough to get you started. But if you want to achieve great places or evolve, really just evolve, there's plenty of stuff to dive into. We have the optimization theory, for example. It could help you in tuning models efficiently. We also have graph theory, and we're gonna be tackling graph theory today. In case you guys are interested, we could tackle other topics in other webinars, but today's focus is really just graph theory. We also have information theory. It really helps you in understanding signal, noise, and entropy. And we also have topology, by the way, because sometimes you're dealing with super advanced models and extremely high dimensional data. So knowing topology might come handy. And that's not everything. Of course, there is more. But of course, it's not a necessity to master them all at once. It depends on where your direction is. Usually, when you dive into AI as an AI junior engineer, let's say, with time, you'll actually get to learn what's your niche, what you're passionate about, what you want to continue in. So it depends on your actual goals and where are you planning to head in. There is plenty of other topics we're not going to be diving into, but they're all found in the resource kit that we will be sharing with you. So we'll be tackling graph theory, and graph theory is really exciting. It's basically the behavior of dots, as you can see here, and lines together. How do they behave together? Of course, that's just a high level overview, just a high level definition, and not the text box definition that some of you might be familiar with. But now let's actually zoom in and tackle what graph theory is all about. So, graph theory is basically a branch of mathematics. This is a misconception here. Some people assume that graph theory is actually part of computer science, but computer science at its core is all about mathematics. Like everything we take was literally just mathematics on paper. So everything is based on that. But we're evolving, and what we see currently is, let's say, or use the term visual mathematics. Plenty of the stuff that we're seeing today is actually literally at its core is mathematics. So it's a branch of mathematics that studies graph, and not the graph that you guys are used to, the bar graph or the pie kind. A graph here is defined as basically made of two parts. We have nodes, nodes being the dots, and we have edges, and those edges connect those dots. These dots, also called as nodes or vertices, are connected via edges, and this is how we write the equation representing that. So you can just think of a graph as a bunch of points, as you can see, or dots, or whatever you want to call it, connected with lines. So, extremely simple, right? And this structure is actually everywhere. It's found in recommendation systems, social networks, even internet routers, and it's even found in biology. We'll see that in a bit. So, it's really not just a bunch of theory and math theory. It's literally a whole new lens to look at complex systems, how they are connected and all. So this is an example. We have the node A, we have the node B, they're connected via an edge. This is called a vertex, and this is called a vertex. This is how a graph would look like. And you might be wondering, why are we even talking about graph theory? Because, and the simplest answer is, data is all about relations. Okay, so there's actually a common misconception is people often mistake knowledge for being data, but knowledge is not data. Knowledge is just raw data that's unstructured, and data is one that you might be able to like build a data set of, one that has clear connections and relationships. Okay, so data here is all about relationships, and we can model that via graph theory. So what graph theory does is it gives us a mathematical way to model those relationships. So, whether it's how users interact on social media or maybe how web pages link across the internet, at its core, it's all just um, graphs in the working. Okay, so it's basically also not just about what's happening, it's also how things are connected. So when we say how things are connected, we're actually tackling relationships. Okay, so they don't just store information like a database, for example. No, they actually reveal the structure. And when you model structure, you build smarter systems. So, some use cases of graphs, we have social networks. You've seen me mentioning social networks, and you're probably wondering what is she talking about. So, in social networks, usually every person is a node, and every friendship, like, follow, is basically an edge. So, Facebook is actually a type of social network, Instagram as well, TikTok, and plenty of the social media applications that you guys currently use. So, what happens is, and graphs are really used heavily in social networks. Graphs let platforms detect communities, recommended friends, and it can even sometimes flag some fake accounts. So they're heavily built on graphs. And it's actually found in GPS, by the way. So you guys obviously used a GPS before. So the cities would be modeled as graphs, roads would be the edges. Let's say I want to go to city X, but I'm currently at city Y. So this is the node I'm in, and that is the node that I want to go to. So I have to find a connection, which is basically an edge between them that would get me from where I am to where I want to go. And we also have website links. Actually, the entire internet is literally behind the scenes just a graph. I'm not really sure if some of you are familiar with the Google's page rank algorithm. That's literally graph theory. It's heavily based on graph theory. And to your surprise, there is also graphs in biology and protein networks. So once again, mathematics doesn't just intersect with computer science or AI. No, it actually intersects with other fields as well. It intersects with biological fields and medicine, and specifically also a new field that rose few years ago, bioinformatics, which is basically just the intersection of biology, data science, and computer science. So they study how proteins interact together or how diseases spread, and they even use them to design some medicine and drugs as well. So as you can see, graphs are used heavily, and they're just powerful for modeling relationships in extremely complex systems. As you can see, graph theory is found in several fields: geography, biology and medicine, AI, and data science. So you might be wondering, what's this hassle about if I can't actually learn how to build a graph? And we'll see a code example in a bit. But to build a graph, if you guys have been following up, you noticed I mentioned the modeling word a lot. So we have something called graph modeling. And graph modeling is the process of translating data into a graph structure. So we have to identify what are the nodes and what are the edges and start building and modeling our graph. So that's literally what graph modeling is all about. So, to actually understand it deeper, let's take a quick example and then we'll be diving into a code example. I'm going to be sharing with you guys the link to a notebook. I'll just drop it in the chat box in a few. So, let me actually just drop it right now. So, what we have here is, I'm pretty sure you all watch Netflix here. We all binge watch Netflix. Basically, what we have is, how can we build a graph for this specific use case? Can someone try and guess? Or just feel free to drop anything in the chat box or open your mic. We have users, let's say me. I'm Sarah, I'm watching, I'm the user, and I have certain movies and I have to rate those movies. Who can tell me what can be the edges in this case and what can be the nodes? Feel free to just drop in your answer in the chat box. So, once again, yes, that's correct. Okay, thanks, Layan and Ra'a. Yes, that is correct. So, before seeing the answer to the example, let's clarify certain things. So, we've talked about nodes and we've talked about edges. We also have something else, which is weights in this case. Yes, sure, you can have a connection between a node and a node via an edge, and you can even put your price on that edge. This is often called weights here in this case. Of course, not all graphs have weights, but some graphs do have weights. They're called weighted graphs, by the way. So the nodes would represent the things, the edges would represent the relationships, and the weights would represent numbers. So this is at its core, uh, just the high level overview of it. Now let's dive into the code example to actually understand deeper what's happening. Feel free to open the link. I dropped it in the chat box, and this is the link here. I'm gonna be sharing the code window. Okay, try your best to follow up. I know that the levels are often different here, but for those not familiar, don't worry, I'm going to be explaining the code line by line basically. So, first of all, what am I using and why did I share the link with you? This is just something on the cloud. It's called uh, Google Colab notebooks. So I could edit the code and just share the link with you, and then you can come back later and see the updated code. Or I could add some people and you could collaborate. So it's a great way to share and write code, specifically um, anything AI related. So what we have here is just a simple example. First off, what's happening is I am importing those Python libraries. So the matplot is used for plotting and visualizing data. It's a famous data science library. So we're gonna be using it to draw the graph. And regarding the network X, it's basically specifically for creating and working with graphs. And it actually lets us define the nodes, the edges, and different kinds of graph structures. Of course, there is more and more. So, what's happening here is I am creating the graph via this line of code. This basically gives us a blank graph. Then I am adding the nodes. Okay. So in this case, Sarah is the user. I'm the user here. And both Inception and Interstellar, two famous movies, by the way, those are the movies in our case. So we chose the nodes. The nodes in this case is me, the user, and the movie names. We have two movies here. Next up, this graph has weights. Why? Because we're trying to rate each movie. Specifically, the user here, who's Sarah, is trying to rate each movie. So the rating, this is the price that we're gonna be putting on the edges. Okay, so this is called the weights. So Sarah is rating the movies via this line of code. She added a weight of 4 for Inception and a weight of 5 for Interstellar. Okay, so this is pretty straightforward. Forward. As you can see, just with a few lines of code, we were able to build a graph. Okay, are we done yet? No, we have to actually draw the graph. So basically, we draw the graph via this line of code, and then we are just styling it. You can, of course, change colors and all. The nodes are styled with pink, okay? Pink for users and blue for movies, as you can see. And the edges are labeled with rating value. And what do I mean by labeled? I'm adding a weight. The way to do it is by putting a label. So, like, this has the weight of 4, okay? And the rest is just to draw the nodes and just plot it, setting the font size, styling, and all. So let's have a look at our output here. As you can see, we have a graph based view of user and movie interactions. So Sarah rated the Inception movie 4, and she also rated the Interstellar movie 5. So this is graph modeling in action, and as you can see, it's pretty straightforward to get started with. You just need a Python background and you need to fiddle a bit with Matplotlib, which is part of data science. So, in case of any questions, of course, feel free to ask. This is regarding our simple code example. Now, let's actually resume. We have knowledge graphs to cover, and then we'll wrap up with Q&A. So if you've got any questions, feel free to drop them in the chat box, of course. So we've seen that we were trying to create nodes and edges, and we had things. But what actually happens when things are concepts and their relationships are facts? What do you think might happen in this case? Nodes represent things, right? But what if things are actually concepts and the relationship between them are called facts? Like, uh, we'll see an example in a few. This is actually a whole another, let's say, something that falls underneath graph theory, and they're actually called knowledge graphs. So we know what graphs are and how they model relationships, right? But their most powerful applications in AI are actually knowledge graphs. By the way, knowledge graphs are fed into many AI models, they're fed into GNNs. So they're extremely important and they're rarely talked about, yet they're extremely easy, by the way. Let's have a look at this example. So we know for a fact that today is the International Day for Women in Mathematics, right? And we know it's on May 12th. And we know for a fact that the webinar we're hosting right now is on the International Day of Mathematics, right? Which is May 12th. And we also know, which is another fact, that I'm giving this webinar, I'm hosting this webinar and going through the slides and explaining, right? So This is also a fact. So all of those are facts. And by the way, this is just a simple example. You can even draw more relationships from this and deduce them. Okay, but this is just a high level example. But of course, you can analyze and deduce more relationships. You can deduce how this node, for example, Sarah, is connected to this node, even though they don't have a direct edge between them. So this is a knowledge graph. It's basically a structured way to represent facts. Each node, a thing, a person, concept, etc. And each edge is a fact or a relationship between those things. And why do we call them knowledge graphs? Because they incite us with knowledge. So we're not storing flat data, we're not storing anything, we're just basically storing connection that tells us knowledge. Okay? So this is just a simple example, of course. Now let's look at the text box definition. Knowledge graphs are structured representation of real world facts. Each fact is a connection between two things. So we've talked about knowledge. Knowledge by itself alone is not helpful, it's useless. But we are able to make use of it via something called knowledge graphs. So it transforms the data that we will have that's unstructured into something that's structured, forming what we know as knowledge graphs. And why do we call them knowledge graphs? Because they are based on existing knowledge that has facts and stuff, and then we are just modeling them via what we call knowledge graphs. Okay, so this is what knowledge graphs is about, and it's actually widely used. It's used in search engines. ChatGPT, by the way, I'm pretty sure everyone uses it. And basically, what happens is it's fed knowledge graphs. So it helps in training GPT or any AI model. They're all fed knowledge graphs. And there's currently an ongoing hype in knowledge graphs and all. And honestly, it's worth the hype. It's also used in chatbots. Obviously, they tap into knowledge graphs to reason and all. So, knowledge graphs are widely used, and they're like the memory of intelligent systems. They give structure to knowledge, which makes understanding and reasoning possible. Okay, so in a nutshell, uh, this is what knowledge graphs are about, and they all fall under graph theory. Now, some people asked some questions in the Google Forms, so we will answer some questions, and feel free to drop in your questions in the chat box as well. We will tackle them. But don't leave just quite yet. We also would appreciate it if you could fill the feedback form. Uh, this is the link. For those interested in receiving the resource kit and all, please make sure to fill the feedback form. Okay, and we'll be taking Q&A and answering some of the questions. I'm just gonna leave the screen. So someone asked, what skills should modern programmers focus on? So there is no right or wrong answer. It depends on your end goal. What are you planning to, let's say, major in or dive in? Like, what's your niche? I would say figure your niche first, then decide. But it's really important to know prompt engineering. We all rely heavily on GPT models and all. So it's important and actually critical to know how to use them properly to get what we want, because if you don't ask the right questions you won't get the right answers. So I would say learn prompt engineering, choose one programming language and stick to it, and of course learn the basics and the fundamentals. And obviously, you have to ensure that you're grasping the important mathematical concepts, the mathematical foundations to actually thrive in such a field because it's deeply and heavily rooted in mathematics. So someone else was asking, how can I get an internship in AI? Of course, there is no right or wrong answer here. It all depends on which field of AI are you planning in diving into. Are you thinking of being a business analyst, a data scientist, a machine learning engineer, a AI engineer? It depends what are you planning on. So what you have to do is choose a roadmap, stick to it, learn the basics, learn the fundamentals, and also work on your people person skills, obviously, and do some lead code or hacker rank to ensure you pass the interview stage. So it's a bunch of things that you could do, but stick to one thing. That's always my advice. Do not go too broad because if you're good in everything, then you're good in nothing. Make sure to find your niche and stick to that and work towards that. Someone else asked, what is the relationship between linear algebra and AI? So I think in we answered that in the session. As you can see, linear algebra intersects with AI, and it's important to know. Some people might argue it's not really important, but it's recommended. Everyone has his own path, but what I would say and what I personally notice is if you actually understand the mathematical basics, then you're able to excel. Paula is asking, what programming language would you recommend for someone who is new to computer science? Honestly, my go to answer would be Python because Python is the easiest to learn. It's extremely easy, like literally as if you're just typing like English. So it's the easiest to learn. But as you grasp the concepts, you sure have to learn other programming language to maybe grasp other fundamentals such as data structures and stuff. So I would say start with Python and from there maybe try Java. Someone else is asking, concepts are nodes and facts are edges. Yes, I think that was from earlier. But yeah, as we've seen, if you're building a knowledge graph, let's go back to this slide. As you can see, we have those edges. This is stating the fact that this is the International Day for Mathematics and all. If you have any further questions, feel free to drop them in the chat box. And I'll answer one last question before we have only a few minutes left. So, someone was mentioning uh, basically uh, how do we use AI and integrate it into mental health? Well, it's outside the scope of the session, but if you're interested in such a session, then feel free to drop in your suggestions in the form, and we could definitely do something on that. Uh, Now, after that, we will be sending the resource kit, so please make sure to drop in your email correctly and all. So that's it for today's session, today's webinar. And I hope you guys benefited a lot, and I hope you really enjoyed the session. If you have any questions or anything, just drop them in the feedback form, and I'll see you soon.